Hi there, welcome back. So, assuming that you didn't close your Fluent windows, if you close it, you can reopen that and point to the path where you download the mesh. So just to remind you, in my case, I have my mesh here. So when you launch Fluent, you're going to point to this directory, and then we're going to open this file. Okay, recall that the .nsh is the mesh. The clean case, you don't have any information, only mesh information. This .gset is a compressed file, and here you have the mesh plus the case setup. So this is the solution just to run immediately, and here you have the solution. Okay, so we're going to start from here. So what we're going to do is that this is our Fluent interface. So I'm going to introduce you a little bit. So what we keep working in more tutorials, I'm going to show you more options, but I'm going to show you the basic stuff. So to read the mesh, the first things that you need to do, you go here in File, Read, and you choose the file that you want to read. So you can read the clean mesh or a case. In our case, it's a clean mesh. Okay, so here I have discard case. Okay, so I already read it, but I'm going to discard, and okay, so it's just discard whatever you have in memory, and it's going to read the new mesh. So this is it. If it doesn't complain, you have your mesh there. Okay, so now that we have our mesh, the first thing is that we need to see some colors, what we have. So you have, it's a little bit complicated at the beginning, the interface, because you will see that you have many options. So you have here this that we're going to call the ribbon. Here we have the vertical pipeline, and here you have also this text user interface that you can here type in commands. Okay, like in Linux or in the command prompt in the OS. So all of them are going to give you access to the same options. Sometimes you can get more options going to a given one, but I'm going to work here with this vertical workflow. The vertical workflow means that you just click here, 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 here to do your case setup. Okay, so this is the one that I recommend as a beginner, but have in mind that you can work in the text user interface or in the ribbon, and here. And very important, here you have the help, and invite you to click there. Okay, the help system is very good. So the first thing is that we read the mesh, and if we want to visualize what we have, you go here and see that you have results, graphics, mesh. Okay, you double click and you select what you want to see. So I know already what I have. Okay, so each of this name that we have here is that when we were creating the geometry, the mesh, we assigned these names. So see that this is what we have. Okay, so this is geometry, and what we're going to do is set up in one of these boundary surfaces flow coming in, coming out, okay, and so on, and the wall. So we're going to do the setup according to these values that we have here. So now that we have visualized our domain, something very important, I always recommend you to click here in scale, and this one is going to tell you're going to see here the domain extension. Okay, because sometimes you work in millimeters, in feet, whatever. So it might happen that you don't have the right unit. So here you can do the scaling. Okay, so you can choose your units, or you can apply a scaling factor or convert. Okay, so I always recommend you check here that you have the right dimensions. In this case, it is okay. The other option that I recommend you always before running, you go here in quality and you evaluate the mesh quality. So here you're going to see these parameters. This is the important one. Okay, minimum orthogonal quality, and this one should be more than 0.01, let's say. Okay, so in this case it's almost a perfect mesh. Okay, but if you get values less than 0.01, 10 to the minus 2, it means that it's better to reduce the mesh. Doesn't mean that you cannot run, but be careful that it might be better to reduce the mesh, and in ansys mesh or ansys Fluent it's quite easy to do that, to improve that. So those are the first steps that I recommend to do. And now that we have done that, we can go and set up the case. So I'm not going to talk about the different methods. Then we have some lectures. I'm going to introduce you to that. But let's do the basic setup. So we start from the top. General. First here you have this option. So see that here you have solver type. You have different solvers, pressure, density, base. So for our case, let's always use now pressure base. Later in the theory, we're going to talk about what is the different, but for us, pressure base is okay. Then also you can choose the discretization. And this is an hypothesis, by the way. So later also we're going to talk about this hypothesis. You can assume that your flow is steady, or you can also assume that if you have a fully unsteady transient flow. Okay, so if you take this hypothesis, steady flow, it means that you don't have any vortex shedding, or you are saying that is something that you can neglect. In our case, steady hypothesis is okay. See that you can also enable the zero gravity, okay? And always here you have the help. So this is our setup. So we set up the basic solver. See also that here you have the option report quality, scales, and so on. So we go to models. Here are all the models, and all these cards that we're following is about this one, turbulence. Okay, so if you click here, you can set up different turbulence models. Later we're going to see what is the difference and so on. So for the moment, what is proposed in Fluent K omega ST is okay. But let's take a look at our case. So see that what we want to do is that here you have inlet, okay, and here we have air, but it's entering with a given temperature. So this is already telling you that you need to enable also some other thermodynamics models. Not only this one, but also see energy. So if you click energy, we're enabling the energy equation, and so on. So if you have multi-phase, radiation, species, and so on, species will be mainly for combustion, structure, stuff like that, you can enable. So in our case, energy and turbulence, and that's all. So we're done here. So each of these options is just to enable different models, additional equations to what we're solving, to the standard Navier-Stokes equation. So we're happy with models, and we move to materials. As it say here, we choose the working material. So we're working with air. So let's choose air. So by default, Fluent propose air, but also you can add new materials, create new materials. So you choose there, change, edit, and Fluent have a nice database with many materials. Okay, so you can have water, whatever, so it's up to you. For us, it's okay, air, but it's very important. Look at that. We have temperature, so we need to enable thermodynamic model. So we can say that the density is constant, or we can add that dependence in density and viscosity, but also thermal conductivity and CP can change. So those are part of the model. So let's say that for viscosity, I want to enable the Sutherland model. It's okay. What is proposed is the three coefficient model. So this is a dependence, viscosity, and temperature. We can do the same for density. So you see that you have many models here, and we can choose ideal gas, which is okay, or you can leave it constant. So these are hypotheses, things that you should do. It's up to you. So in this case, let's say that I want to use ideal gas. CP and thermal conductivity is okay to leave it constant for this temperature range that we're using. They are not going to change, but it might happen that you will need to add another dependence. So see that here you have many models. So now that we choose that one, it is okay. We enable the model. This is the fluid. Have in mind that here you have the solid auction. The solid auction is when you have problems like conjugate heat transfer or fluid structure interaction, that you need to define the material, not the solid material. In this case, we don't need to define that. So there is no need, but the same stuff that you can choose different materials. But this is in case that you need to define that. In this case, no need to do that. Even if you have it here, it's not going to be used. So now that we choose the materials, we move to the next step and see that everything is vertical, no? It's sequential from here to here to here, cell-zone conditions. So this is your whole domain, everything that is within all this domain. So as you click there and you go into edit, you can assign the material, but some other options. So these are all models, okay, and sorcerer, stuff like that. So we're not going to select anything, but see that you can add more options to make more complex your physics. What is interesting is that here in material name, you can choose your material. So it might happen that you have different materials. You need to pick to choose the right material. And just to show you, let me create another material, new. And let me say that I want water liquid. So I created a new material, I selected, and see that you have it here. So as you go now here, edit, see that you can choose water or air. So we want to work with air, so be careful that you need to select your working material. So then in cell zones, you have many other options. We're not going to go into details about those options. Always remember that you have the help. Also going to give you a link to download more advanced training material. So as you click here, operating conditions, you can set up your operating conditions. So as you want, also you can enable gravity here. As you enable, you give the gravity vector. Okay, reference location for reference pressure now. And this is your working pressure. So as you put here this value, atmospheric pressure, later when we give boundary conditions, everything is relative to this. Okay, so I recommend you to work like this. You define a pressure level, and then when you give boundary conditions, everything is relative to this. And that's all. Now we move to boundary conditions. Boundary condition is in each patch, in each of these surface boundaries that you see here, we're going to give an input value or output value. So see that we have inlet large, which I know it will be one of these. So let's say display mesh, and let me see which one is. Okay, so this is the inlet large. So this one, we're going to set velocity. So as you click there, so as you are here, let me go inlet large, and let me go back here. So here we have velocity and temperature. So see that inlet large, and you need to choose a type. You have many types here. For us, the type that we're going to choose is velocity inlet. But as you know, the mass flow, you have there mass flow, and so, or the pressure, you have it there. So velocity inlet, and now you can give the values. So see that I go here, you have different options. For us, it's magnitude and normal to the boundary. And the value will be, if I will recall, 3. Let me see, 3. Okay, so you put it there. Then thermal is the temperature. Okay, so the temperature by default is in Kelvin. Okay, you can convert it, but also you can change. So if you don't like to work in Kelvin, you go here in units. You go temperature here, and instead of Kelvin, put Celsius, and there you have it. Okay, so but it's not a biggie. So 25, apply, and that's all. The other thing that I didn't mention here and is you have more models, these tabs are going to be enabled. In this case, we don't have any of these models, so they are disabled. So see that in momentum here, you have this option related to the turbulence model. So we're solving additional equations, okay, for the turbulence model, and requires values. For the moment, use the default values, but there is a logic behind this that later we're going to see. But use these default values are okay. And we do the same with inlet small. So it's a velocity inlet also. It will be magnitude normal, and let's see this 555. Okay, default values for turbulences are okay, and 55 here. Apply, and we have it there. Then interior fluid, nothing to do this is the internal cells. Okay, so it's interior by default, nothing to do there. So then outlet, okay, would be this, and in the outlet we are just, it's a natural boundary condition. Okay, it's like extrapolation. So you're going to have a behavior here, and the behavior that you have here is going to be extrapolated, it's going out. But it's important also that here you need to fix also a pressure value. Okay, so we put pressure 0. So it's a pressure outlet. you click edit and see that it's already fixed. You choose these options, use the default options, also for thermal, and this is important. So when you see backflow, when you have boundary conditions and in particular outlets, and you see backflows, that means that it might happen that in that outlet, might happen that you have some vortex shedding, and you can have some flow coming back into your domain, and that numerically speaking can give you some problems. So backflow is just to do a specific treatment, what to do in case that you have flow coming back. So in this case, see that if you have flow coming back into your domain, what is going to happen with the temperature, or total temperature in this case? So you can say that it can be the average between these two. So let's say, let me fire something like 40 Celsius, okay? But it's up to you, okay? So this is on a specific technique. So all the time see here that you have backflow pressure specification, okay? So you can go for a static or total, it's up to you, okay? So let's leave it total, and this is it. Then we have also solid, which is the wall, and let me recall that as you plot the mesh again, see that solid is the walls. Okay, so if we go here, solid, see that is a wall. But also wall can take options. So let me click edit and see that in a wall, okay, you can move a stationary, moving wall, you can specify shears, no slip means that you have boundary layer, you can give roughness and so on. But as you go into thermal, see that you have more options. So as we give heat flow 0 means that it's adiabatic, but you can fix temperature, you can give a heat flows, convection, you can define radiation and so on. In our case, this is okay. And that's it. We define all our boundary conditions. So after defining boundary conditions, we click here. So for the moment, we're not interested in this, 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 and we're not interested in this. So we're done with the case setup. Just let me say something about reference values. So in reference values here, you give reference values to compute coefficients. That's all. So Fluent is computing forces and so on, but many times you would like to compute coefficients like pressure coefficient, lift coefficient. So these are the values that you use to normalize everything. That's all. So usually you can say that let me use the inlet values, inlet small, so see that it's setting the density that corresponds to that temperature value, the velocity that you set there, and so on. So this is just normalization. So now that we are done with the setup, we move to solution. This is the numerical method that we're going to use to solve the Navier-Stokes equation plus additional closure models. So if I go here into methods, I recommend you, so we have a lecture dedicated now just to talk about these methods. There are many methods. Also remember here, help. So very good, the help in Fluent. Let me click to show you. But in any case, that what is Fluent proposing, it is okay. So I always recommend you to choose what Fluent proposes, the best option possible. So here you have the help if you want. It's very good help. So let's use what Fluent proposed by default. Same with controls, okay? Use what Fluent is proposing by default. Report definitions. Okay, here you can create monitors. Okay, so stuff like computing mass flows in boundary surfaces, forces, and so on. So here you have many options, and just to show you, I will set up one monitor. So if I go here, new, and let me say that surface report, and I want to compute the mass flow, and see that I want to compute mass flow here, here, and outlet. Now my inlets and outlets. You give it a name. I will call it MF1. You can compute it per surface. See that you have 3 surfaces, so you are going to see 3 plots. Or if you don't select this, it is the summation, will be the imbalance. So as the method is conservative, should be 0. So I will show you, and see here that you can choose to report to a plot and save to an ASCII file. So I will leave it like this, and see that I created the monitor. Okay, let me create another one, the same stuff, but now per surface, okay? Just to show you the difference. And then it was this tree. You leave it like this, okay, and that's all. So you have your monitors, and here you have now this is related to whatever you created here. So report files and monitor. That's all, okay? So you have many options there, so feel free to play there. As you see, you can create very, very complex stuff now. So average, you have integrals and expressions and so on. We go here now, cell registers, nothing to do for the moment. Automatic mesh adaptation, nothing to do for the moment. Initializations. So we give boundary conditions, we need to give initial conditions. Okay, so inside the domain, we need to tell what is the starting point. Okay, so Fluent also gives you different actions. You have two actions here, but also in the text user interface, you have different actions. So in this case, I always recommend to use hybrid initialization. Okay, so it's a method that Fluent automatically finds the best conditions. Okay, here more options, you have more options. On, if you want to know what is happening, always here help. So I will click initialize and see that we initialize the solution. And that's all. We have an initial condition, calculation activities. For the moment, nothing to do here, but this is to do things in an automatic way. So for instance, you can save your solution every given iteration. So I can say save the solution every 50 iterations. You click here, edit, you have different actions, okay, the location of the file, whatever, and here and so on. Okay, so for the moment, probably this is the important one. Know that this might happen. I know your computer crashed and if you didn't save your solution, you lost that information. Instead, here every 100 iterations, it's going to save the solution. So if something happens, you know that you're going to have something there, and the solution will be saved in this folder where the folder that you gave at the beginning, where you have the file located. So let's say that we have that. And at this point, we're ready to run. So see that we're running here, and this is a steady method, a pseudo transient method. So see that the only thing that we need to give here, the maximum number of iterations. Okay, so Fluent is going to iterate until reaching this maximum number of iterations. Usually 1,000 is a good value, or until it reaches the convergence criterion. So the convergence criterion by default is 10 to the minus 3. So it's an industrial value, and that is defined here in monitors. Let me go back here, residual, and see here that you have it here. Okay, so energy usually is a low value, but then the other is 10 to the minus 3. So if you want a lower convergence criterion, it's up to you, but usually this is an industrial standard, so leave it like that, but you can change it. So this is it, okay? We can't, at this point, we can run. We have set up everything. So before running also, before running, we can save the case. So as you go here in File, Write Case and Data, and I will call it Test1. See that it's saving the files here, and it's saving the cast file and the dot file. Okay, so I save it. Let me see. Tutorial Fluent. Okay. Here we have test1. I save my two files there. Okay, so at this point I'm ready to run, and we only need to press calculate. Okay. So as you press calculate, here, off you go. So that is running, you have all your monitors. So your residuals, later we're going to talk about these residuals. See that this is the mass flow, the summation, and mass flow by individual boundary surfaces. And see that it is conservative about 0. You can stop the simulation. So as you press here, you see that you have the stop here. As you press stop, it will stop the simulation, and then you can keep iterating, okay? So let me show you. Let me go here and let me put this one like this. So see that here we reach the tolerance, the final tolerance. So I put a lower value, see that it stop, and it will stop, and then you can relaunch. Okay, so it will start from the previous iteration. So in our case, it reached convergence quite fast. So let me put here 4, calculate, and see that reach convergence or the maximum number of iterations. So you can put a very large number there, it's up to you. So now that we have a solution, and let me go back here. So see that this is your mass flow, okay, the summation of all the mass flow. So it's conservative, should be something close to 0, and here you have it by surface. But now we can see the colors, okay? So now see here that you have the tab called results. We can go to results and visualize the solution. So see that you can access all your surface and solid also. So I click here and see that this is the pressure at all your surfaces. You can also choose velocity and see that you have velocity. Remember, at the walls we have boundary layer, so it's 0, so that's why you see 0, but then you have the values of the patches there. So if you don't want to see the wall, the select, you have it there. For instance, you want to change the scale, you don't like that scale, let me put here 5, and this one, click to range, deselect there, and you have that. Okay, so you can choose also temperature, okay, auto range, you have it there. So see that at the outlet, the temperature there. Okay, so here is hot and this is the mixing. So this is the basic post-processing, but let's say that you want to visualize in a cut plane here in your domain. So you need to create that cut plane. So as you go here into surfaces, choose new plane, and see that you just choose where you want that plane. So I don't want that one, I want this one. And that is perfect. Okay, so you can create as many as you like. So we created that plane with this name. And see here that you have many options. So you can create points, lines, planes, isosurfaces, now surfaces with the same value, isoclips, clips with the volumes with the same value, and so on. Okay, but for us, isosurface is okay. The plane is okay. And now we have this plane and we can access that here. So let me go here. I press new. And see that you have that plane there, and I can plot there the temperature, and I can plot also that in the other patch. So see that you have it there. So now I can plot velocity there, and see that you have your velocity there. Also you have vectors. So the vectors, I will put it in this plane, and see that you have the vectors there, and see that you have this nice recirculation region there. Okay, so see that here, kind of the boundary layer. See that you have the scaling there. You can play around with those options, how you color. So for instance, let me go path line. We can release path lines from this patch, the inlet small. And see that these are the path line or string lines that are following the flow. And you can color by different variables, so by velocity. Have it there. Also you can animate scenes, so we put it like this. So these are just colors, okay? So, but give you a good insight what is happening. Okay, so feel free to play with those options. Be careful that this is a small case now, so it's quite fast, but if you have very large cases, doing this stuff can be very time consuming. So for instance, you can use this option like skipping pass lines just to use less memory. So this is it, the basic color. So feel free to play with all these options to visualize. For instance, also you can save this image. See here that you have also this ribbon with many options, and you have this one here. You have the camera there, save picture, and that's it. Save, and let me save that in desktop. And there you go. So then you can put in your report, whatever. So this is how you save the image, okay? So there are other ways to do the post-processing, more sophisticated, prettier than this, but this is the basic stuff. Now that we saw colors, it's also important to compute integral quantities, okay? So this is graphic just related to colors. Later also we're going to see what is this graphic plots, scenes and so on. But I want to go into reports because here's where we compute those integrals. So see that here, for instance, we have these fluxes. So you want to compute fluxes, select here and compute, and see that you have it there. So see that the method is conservative, what is going in is going out. So see that it's a close value, close to 0. You have also the fluxes, the thermal fluxes, so everything should balance, and so on. So forces, you can compute forces, obviously at walls. So you need to define a wall and you can compute, and then you can give the direction vector. Okay, so you have forces and coefficients. The coefficients are normalized using the reference values that you define here in setup. Okay, and then here, for instance, you have surface integrals. Okay, so for instance, I can select outlet, and well, it's up to you what you want to compute. So I want to compute the average of temperature. Compute. And it's telling you that there, the average temperature is this one. So there are many, you can compute the minimum, maximum value, you can integrate, you can compute standard deviation, uniformity index. In case you want to know what are those, just always click help and you have the information there. Area, weighted average, so the average weighted using the area, okay, so you have it there. Or the weighted average using some other quantity. So let me see where, okay, custom, this should be this. Okay, so you average using a given vector, and I then access that. Mass weighted average, okay, so this is weighted with density or temperature and so on. So it's up to you what you want to do, okay? So this is it, okay? So this is the basic case setup. So I invite you just to redo this one, play around with the options here in graphic visualization, okay? Compute different integrals, and feel free now to change here boundary conditions, different values, or enable, disable models. In our case, try to disable the energy model, but also try to disable the turbulent model. So go from one of these turbulent models, go to laminar. Laminar means that you are not using a turbulence model. Doesn't mean that the flow is laminar. It's just the turbulence modeling is switched off. So, and then InVisit, no viscosity. So try to compare InVisit, laminar, and K-omega-ST. So remember, for each simulation, you will need to save the files with a different name. So see that in my case here, I already have here InVisit, laminar, and turbulent. And compare the cases. So try to reproduce these results here. So see that here you have the value at the outlet of the average temperature. You have the mass flow. You have this y plus value. Okay, this quantity is important, very important in turbulence modeling. Okay, we have here also turbulent viscosity, temperature. So try to reproduce this. As I say, very basic case, but just to introduce you with the graphical user interface. Then we have more advanced tutorials, okay? So thank you very much for your attention, and see you next time. Bye.